Okay, welcome back, everybody. Give me 1 second, let a couple of people in. All right. Just a couple of announcements. If you need to see me, I have set aside Tuesday and Thursday between 3 and 4. So, for office time, I'm not required to have, as being a part-time instructor, I'm not required to have office hours, but I offer that because I know students occasionally need help. So give me a call. After those hours is a little bit difficult because Tuesday and Thursday I teach a 1 o'clock class and a 4:15. So I'm trying to slip those in, slip that time in between 3 and 4 between those two sessions. And then on Friday afternoon, I teach from 1:15 to 4. So that's tied up too. So if you need time, those are the best times. Last resort, if those doesn't work for you, shoot me an email. I'll see what I can do. Okay. Let me see what else. Any comments, questions you may have? No, what I'm going to do is we'll finish up chapter 3 today. It's fairly short. And then Thursday, you have the exam. Okay, chapters 1 to 3 online. I sent an email about 24 questions, most of them multiple choice. There are some that you need to fill in the answer, short answers. Okay. So if on Thursday, if there are questions about chapters 1 to 3, no problem, we can talk about them. If not, I will continue with the chapter 4. Okay. All right, any questions? Now, well, let us begin with this chapter 3. Now, in this particular chapter, we're going to be doing conversion. We're going to do some mathematics, nothing complicated, as I stated, add, subtract, multiply, divide. Most of it multiply at this point here. And we're going to talk about a technique and how to keep your units all set up your problem so that you follow the units, and it allows you to assure you that you set the problem up properly so you get to the answer that you're searching for. Okay, we're going to talk about that. Now, I did give a couple of papers on metric. I mean, in the module, this particular module, but some additional papers on the metric system to help you out. If you've not had a chance, do read them. I think they're good resources. Because a lot of us who didn't really grow up with the metric system, sometimes we have a challenge with it, and that's okay. I did mention that we've been trying to convert to the metric system since I was like in elementary school, so they still haven't done it. Anyway, so we got to work with both metric and English. All right. So the units for length, mass, volume, and time. So time pretty consistent. Units is seconds. The most common, it doesn't mean that we don't use hours and so forth, but the standard unit in the metric system is second. With respect to length, we use meters with the symbol lowercase m. For mass, we generally use grams. Does not mean we don't use other ones like kilograms, milligrams, etc., but grams is the standard one, lowercase g. And then for volume is liters, capital L. Okay, now I did talk about this in the PDF file that I sent to you with respect to prefixes, metric prefixes, where the K represented kilo, which meant it was 1,000 times larger than the base unit. Deci was 10 times smaller, and I used the term to help you out, where how many years in the decade? 10. Okay, so it's 10 times smaller. How many years in the century? There's 100, hence 1 century for C, hence centi as the prefix for 100 times smaller. And then M for milli for 1,000 years in the millennium. So it's 1,000 times smaller. And then I introduce a new one, has looks like the letter U, but it's a lowercase symbol for micro. Okay, which is 1,000,000 times smaller. And these prefixes can be utilized for all of the other, for mass, for volume, and length. Okay, so, all right. So we use the example of metric conversion where we said 1 meter. You know, we know that C stands for century, stands for 100. So therefore, in 1 meter, there are 100 centimeters. Okay. And 1 meter equals to blank dm, which is decimeters. And you think, okay, how many D for decade? There's 10. Okay, and there must be 10 decimeters in 1 meter. 1 kilometer, the K is for 1,000 times greater. And so in 1 meter, there must be, in 1 kilometer, there must be 1,000 meters. Okay. Just like if there were 1 kiloliter, there'd be 1,000 liters. And 1 meter, there's a unit mu, which stands for micro. So there are 1,000,000 micrometers in 1 meter. And then finally, M for millennium, 1,000. There are 1,000 millimeters in 1 meter. Okay. So we'll be using these a lot. And these are conversion factors. 1 meter is equal to 100 centimeters. There are conversion factors that we can set up as a ratio with either centimeters in the numerator or centimeters in the denominator. One, either way we need, depending on the problem that we need to do. Okay. Now, the method utilized in your textbook is called the factor label method. You may find it named by other names and other techniques. It's basically the same thing. Okay. And that is keeping track of the units. Okay. Identifying what are the units that you need to look for, what you're trying to calculate for, what you're trying to find. Okay. Then identify what you are given from the problem. That's your starting point. So you got a starting point and you have an ending point with respect to the units. And knowing that, now you can put conversion factors in between the two to get you to the units that you need to determine. Okay. And that's what we do here. We add these factors in between them. We set those up as fractions, as ratios, and we set them up with the units in the appropriate spot so we can cancel them out and get to the units that we're looking for. Okay. And then you do the math, and then depending on your sig figs that you started on, okay, and how many you need, then you round up your final answer with a proper number of significant figures. Now, a word about the term when the question in the problem says, give your answer in the proper number of significant figures. Now, when you see that at any problem, the next thing you should do is this. 1, am I multiplying and dividing, or am I adding and subtracting with respect to the mathematical function? Okay, now why do I want to do this? Because I treat sig figs differently, as we talked about, when it comes to multiplying and dividing. When we multiply and divide numbers, we always give the answer with the least number of significant figures that our starting numbers had to begin with, our measurements. Okay, so again, the whole drive in both cases is to give an answer no more accurate than the least accurate number that you start off with. When we add and subtract, we concentrate on decimal places. And again, you identify which number has the least number of decimal places. So therefore, your answer, regardless of the number of significant figures, your answer, when you add and subtract, contains the least number of decimal places. Okay, and that is, again, presenting your data no more accurate than the least accurate number you worked with. So that's the point here. Think when they say proper sig figs, determine what mathematical function you're doing. All right. So we suggest that you start off with what is given, write down what is given in the word problem, and then write down what units you're looking for. Okay, that's your track of where you gotta go from where you're at to where you gotta go with respect to the units. Now, sometimes, at times you'll be asked to show your work. Well, what we mean by that is the following. Is, you may have like, some problem where you set up all these conversion factors to get your answer, whatever the answer would be. Okay, you're multiplying by some number and you're doing all this. That is showing your work. So for example, a typical problem may be where, let's say, 5 points, okay, total. Well, normally we break it up, we say there's 1 point for the correct answer. And the remaining 4 points is given for the rest of the problem, how you show your work and how you set it up properly, okay? The point being is this: if you don't show your work and you don't show your work and you give the wrong answer, then there's no credit that I can give you. You just end up with a 0. All right. Now, the other aspect is this: what if I just give me the correct answer? Okay, with the units, that's fine. You can do that, but I can only give you 1 point for that because you didn't show me the work. Okay, remember the rest showing the work is worth 4 points. And then by the same token is this: let's say you typed in the wrong numbers in calculator and you got the wrong answer. Okay, well, I can't give you that 1 point, but you set it up properly with respect to the conversion factors, and obviously there I would give you the 4 points. Okay, you see how that works? So I would give you full credit, not full credit, the credit for the showing the work if you present the answer which is incorrect, because I don't think you should be taking points on 0 if you give the wrong answer, and yet you demonstrated that you know how to set the problem up. It could have been a simple thing if you're pushing the wrong number in the calculator, and that's why you presented the wrong answer. Okay, so keep that in mind when you are working on the problems. That showing work means showing how you got from one unit to the other. All right, so let's do some practice. Okay, so here we got a problem right here. Here's a simple problem. Okay, yes, I know you may already know how to go to the answer right away, but you got to show here in this example. All right, so first step is this: identify what you are given. You are given 2,389. That's the given as your textbook places. Okay, identify what you are looking for. What are you trying to find with respect to units? Well, we're looking for units of liters. So we identify that. The other aspect is this: identify your sig figs, because you have to keep track of that. Remember, everything here throughout the semester, sig figs will always be looked at. Okay, not it's not going to be we just talked about the topic and then that's the end of it. It's not. So significant figures will always be utilized throughout the semester. So here we got 4 sig figs. We know that. Then the other thing is write down what I know. Well, unit wise, we have to go from liters to milliliters. So one factor that I'm aware of is that there is 1,000 milliliters is equal to 1 liter. I may need that. Okay. All right. So once we've done all that, we write down what we are given. So I got 2,389 milliliters. Okay. That is what is given. We're going to put factors in here, or factor, sometimes more than one, sometimes only one, but we're going to put it in there so that the units we're looking for is liters. Okay, so that is what we're looking for. Fine, that's why I write it down so I guess my mark on my little trail. Then I go from point A to point B, so I don't lose track of what I'm trying to obtain with respect to unit. All right. So now the factor, what do I do with my factor? Well, just the fact that you just set it up like this tells you that milliliters to be in the denominator. Why is that? Because when I multiply this factor with 2389, I want my units of milliliters to cancel. Okay. Sometimes you don't see that. Well, I'll tell you what, take a whole number. You know, you can convert it to a fraction by simply doing that. If this is better for you, then do that. Okay. All right. So then I know from up here that I had the factor liter, and that there are in 1 liter, there are 1,000 milliliters. And so now when I do the math on the units, I can see the milliliters cancel. Guess what? I end up with my units of liters, which is what I'm striving for. So now I have set up the problem properly, okay? And now it's up to you to plug it into the calculator and do the mathematics. And when you do that, you should end up with the following answer. Okay, that's setting up to 0.389 liters. Okay. Now the other aspect is, well, what? Does that answer make sense? Okay, just plugging the numbers in the calculator is not enough. You got to take one more step and look at the answer and say, does that number make sense with respect to the mathematics that I'm doing? Okay. And looking at this, that I'm going from milliliters to liters. So I would anticipate that the magnitude of just the number, regardless of the liters, would be smaller than the magnitude of milliliters, okay? Because I'm dividing by 1,000. So here I got 2389, I end up with 2.389. That is consistent. If you inadvertently put the 1,000 up here in the numerator and then did the math, well, that doesn't make sense with what the units that you're striving for. You're going to have a much, much, much greater number than you started with. The point of this is to look at the answer, okay? And don't be quick to assume that that is correct. You know, take it one more step. Does that answer look correct? All right. So here we have how many kilometers are in 12,300 centimeters. All right, so let's work this through stepwise. What we are given is centimeters with respect to units, and we're looking for kilometers. Okay. And so I write down what I am given. And then over here, I write down the units that I am striving to get, kilometers. So it looks like I'm going to need units here to convert. So I'm still within the metric system, meters and kilometers. So unit wise, I'm still within the metric system. Well, to get the kilometers to centimeters, the common unit that these two have is meters. I know that in 1 meter, it is equal to 100 centimeters. I also know that in 1 meter, and 1,000 meters, excuse me, that is equal to 1 kilometer. Okay, so my commonality here, unit-wise, is my meters. So it looks like I'm going to need 2 factors here to get me to kilometers. All right, well, the very first unit, I need some unit that has centimeters in the denominator. Okay. Well, that puts the first one up here. So I got meters on top and 100 centimeters in the bottom. Check my units, centimeters cancel. Okay. So my second factor, I have to set it up to get rid of meters. Okay. And I end up with kilometers in the numerator because that is what I'm looking for unit-wise. So that's my second factor, where I put 1,000 there and 1 kilometer. So I double check my units. Okay, everything looks good. Now it's a matter of you plugging in those numbers into your calculator to get the answer. Okay, note the sig figs. I got 3 sig figs here. So the 12,300. Okay. These factors are all exact numbers and therefore do not play a role in determining the sig figs. But now it's a matter of doing the mathematics. You may clear it. Like that, and you end up with 0.136 kilometers. 4 is equal to 12,300 centimeters. Okay? And that number, again, it's reasonable because I'm starting with 12,000 centimeters. I need to go to kilometers. So the magnitude of the number is going to be smaller. Okay. If I inadvertently flip those units over, where I got the 100 and the 1,000 in the numerator, well, I'm going to have a very, very large number, which is not consistent with going from centimeters to kilometers, right? All right. Now, here's some more factors for you in the English units. Obviously, these are not all of them that we utilize. If there's more out there for you to utilize and you need, no problem, by all means. You know, I mean, you can even have, you know, like 5,280 feet equal to 1 mile. Okay, or any combination thereof. Now, notice something that you probably some of you may have picked up, that you've noticed the one with the 2 factors here. I can make from those 2 factors 1 factor, where I get 1 kilometer is equal to what, 10,000 centimeters. Because just multiplying the units in here leaves me with kilometers per centimeter. So I could have 1 unit conversion factor to give me this directed from centimeters to kilometers. Now, only if you see it, you're more than welcome to do it. If not, until you become comfortable with it, put as many factors that you need out there until you can see the connection, and then you can start combining units. All right. Or like, for example, I mean, obviously we know that, well, if you don't know, but 3 feet to the yard, but we also know that there's 30, 36 inches equal to 1 yard, right? And combine it like that. So any combination thereof. But I can't emphasize it. If you don't see it, just use as many units as you need to get from point A to point B. We talked briefly about this. This is the one for English units and quarts and gallons, where the big G, there's 4 Q's within the big G, which is 4 quarts for the gallon. And then there are 2 P's within the quart, which is 2 pints for the gallon. And then within the P, there are 2 C's where represent 2 cups per pint. Okay. So you have conversion factors there within the English unit. Question may be, how many gallons are there in 44.5 cups? Okay, so we write down what we are given, and we write down what we are looking for unit wise. And now that tells me how to set up the problems that I need to set up with respect to my factors. And so I know from the conversion factor that in 1 pint, there are 2 cups. So I set that up with cups in the denominator because I want cups to cancel out. Now I'm in the units of pints. Well, it's not gallons. I got to get to gallons. So I know there's a connection between quarts and pints. So I can get rid of the units of pints. So I got rid of cups with my first unit. Now I find a second unit factor to get rid of pints, and there's 2 pints per the quart. Okay, and then finally, I know that there are 4 quarts of the gallon, and I set it up with the quarts in the denominator so they can cancel with the middle unit, the middle factor, and there I got it all set up. All my units cancel up, and I'm good to go. Now it's a matter of yourself plugging in those numbers. Now, this factor here, whether you separate them in 3 factors or you put them together, because can you see how the connection between gallons and cups is 4 times 2 times 2. So 1 gallon is equal to what, 16 cups. See, I can combine that to that unit. This is what I mean by some of the units I can combine to make 1 unit. And that's perfectly fine. Okay. To demonstrate that as how you got from point A to point B. And any combination, I could maybe just work with the first 2 here and go from quarts to cups, whereas there are four cups in 1 quart. So, but if you don't see that, just keep it each one separated and use as many as you need until you're comfortable with all these factors. All right, next one is how many inches in 3.5 yards? Oh, sorry, I forgot to show you the answer is 2.78 gallons for 44.5 cups. Okay, keep track of your sig figs. Obviously, the 3 factors are all whole numbers and therefore exact numbers, and therefore do not play a role in determining the number of sig figs. Okay, next one is we're going to go from yards to inches. So my first conversion factor says I know there's 3 feet to the yard. Okay, and I use that because that gets rid of my yards and it puts me in units of feet. But the question was to get me into units of inches. All right, so I need some more factors. I got 1 factor here that I know there's 12 inches to the foot. Okay, and so I have now gotten rid of my feet units, and I'm now in the units of inch, which is what was asked of in the question. Okay, so do the math, and my answer is 126 inches. Now I ask you, would I present that number as 126? Is it good to go to give that as my answer, or do I need to do anything different? Sig figs, exactly. So my answer should be, and how many sig figs? That is correct. And so my answer of 126 would be my 2 sig fig position for my answer is right there. Okay, and like we've been doing before, I look at the neighbor. The neighbor is greater than 5, so that means a 2 gets bumped up to 3. And remember that 6 now gets converted to 0 because we're in the magnitude of 100. And so that becomes 130 inches, not 13 inches, because we remember that number is in front of the decimal point, and therefore any numbers in front of the decimal point get converted to 0. Otherwise, we change the magnitude. All right. Now we give you 3 conversion factors to get us from English to metric. Okay, the 1 inch is equal to 2.54, and then the 1 pound is equal to 454 grams, and 1 quart is equal to 946. Exactly, Thomas, you are correct on that, and just saw the answer. And then 1 quart is equal to 946 milliliters. Now, the second 2 are measurements and approximates. Okay, and therefore could be a factor. I repeat, if you use the last 2 conversion factors, they could be a factor in determining how many sig figs your answer has. Okay, so both of them have 3 sig figs. And if you were multiplying with a number that had 4 sig figs, by either one of these factors, then your answer should have no more than 3 sig figs, because these two are approximate. By convention, be consistent with the rest of the world, so to speak. It is the 1 inch is equal to 2.54 centimeters is treated as an exact number, and therefore would not play a role in determining the number of sig figs. Okay. Some scientists have a different opinion of that number, but I want to continue to be consistent with the rest of the chemistry department. But remember, the 2.54 would not play a factor in determining your sig figs if you use that factor. Treat it as any, like 1 meter is equal to 10 centimeters. It's an exact number. Okay. And they're given to you during exam simply because they're on the table, the shapes table. So you have them there readily available to you. Okay. Now, how do we use this? Well, question says here, how many pounds are in 248 grams? Well, pounds to grams, second entry there, 1 pound is equal to 454 grams. All right, so we just set up as follows. Our units grams cancel, and we're good with respect to units of pounds. We have 3 sig figs in the 248 and 3 in the 454, excuse me. Therefore, our answer should have 3 sig figs. Okay. All right. Now this is a little bit longer and gives you an opportunity now to use your scientific notation function of the calculator, because 3.54 times 10 to the -3. Remember, look at that exponent. Always keep track of the exponent. Sometimes students tend to forget looking at the exponent. In this case, it's a -3, which tells you that that is a number much less than 1. So when you input in your calculator, you got to make sure that you are inputting it correctly. And so I'm going to quickly share my calculator. And if I'm going to input the calculator using the Windows calculator, I'm going to input 3.54. So I go 3.54. And then in this case, I'm got to get to the scientific calculator side of that. Okay, let's clear this up. 3.54. And then I'm using the EXE button. You could be using the double E button or the X10X power button, depends on your calculator. 3.54 EXP button, and then 3, and then I want to toggle it to the negative. So that is how I would input 3.54 times 10 to the -3 in the Windows calculator. Okay. And that, don't forget that toggle. Also on your calculator, check your button on the calculator to help you with the toggle button. All right, so we set this up, we write down what we're given. Okay. Then I know, based on the conversion factors within the metric unit, that we have the 1 meter, 1,000 meters, 1 kilometer, and 100 centimeters and 1 meter. And so these two factors have the meter in common. So I use them. Yes, I know I can combine them, but I use them separately until I get confident in how I can combine them. And I check my units. My first factor gets rid of the kilometers. Okay. My second factor gets rid of meters. And then my metric to English units, which is 1 inch is equal to 2.54 centimeters. I utilize that at the end, setting it up so centimeters in the denominator, so I can get rid of centimeters. But with respect to unit, I am now in the right spot. Okay, it's been set up properly. Now, also, you might be tempted to take the inverse of one of the 254 and make that into a fraction. My suggestion is leave these numbers whatever they are. If it's 1,000, put in the numerator as 1,000, or put in the denominator as 1,000. Try not to change things around. Leave those numbers alone. I've seen too many answers that were out in left field because students did that and forgot what exactly they did. Okay, so just leave your numbers where they are. Stick them on numerator, denominator as needed. Now everything's set up properly. Okay. Once you know you set up properly, like I said, 99% of the time you got it right. That 1% depends on you because you're in control of the buttons for the calculator. Okay. All right. Once you do that, all the three factors are exact numbers. So therefore our 3.54 has 3 sig figs. Our answer should have 3 sig figs. Okay. Next one is we got 2 liter soda bottle. When I convert the 2 liters to quarts. Okay. And so we know that in 1 liter, there's 1,000 milliliters. I use that to get my liters into milliliters, because I know this conversion factor, there is 946 milliliters in 1 quart. Now, if you recognize that, you also could see that there is 0.946 liters in 1 quart. You see that? This is what I mean by once you get comfortable with the whole process, you can start making shortcuts, but don't do that until you're comfortable with that. And so here my units of millimeters get canceled out. I'm looking for quarts as per the problem asking. Okay, I have 3 sig figs because remember the 946 is not exact, but my 2.0 is 2 sig figs, and my answer should have two sig figs. If the 2.0 was written as say 2.000, then that has 4 sig figs. Okay, but the 946 has 3, so my answer should be with 3 sig figs, because remember 946 is a measurement. It's not exact and could be a factor in determining how many sig figs your answer has. There are some problems like that in the homework, so keep an eye out for that. You use the conversion factors that we give you. Yes, there's tons of different conversion factors out there on the internet. The answers on Canvas are based on our conversion factors that we present to you. Okay. And the answers, we type in the answers, what the correct answers are. If you use other factors, you may be off by 100th place or something, and Canvas does not have AI. It's not AI. It won't recognize as correct and therefore count it wrong. Okay, so use our conversion factors, and if your answer, you are 100% correct, I have no problem with checking it, making sure it is, and giving you credit. Because keep this in mind, if you type in an answer in Canvas and you inadvertently add a space, a simple thing is a space. Canvas treats that space as a number and would be incorrect, and would treat it as incorrect in Canvas. Okay, so don't try not to complicate things, just use our factors. The same is true when we start talking about atomic weights. Use the atomic weights from the periodic table that we supply. All right, so much for that type of calculations. You're going to see a lot more. The main point of this is using the units to keep track from going from point A to point B. We're going to utilize the same system with respect to calculations of chemical reactions. We're going to calculate the amount of quantity of reactants and determine how much product we can get. And we're going to set those up just like we just did with ratios, with factors. Okay. All right, so let me kind of shift gears a little bit. And we're gonna kind of jump into doing calculations with density. But before we do that, we're gonna talk about volume a little bit, okay? Now, there's two ways to obtain volume, or to measure volume. I'll go with the first one, which should be this. The first one is real straightforward. In that if it's a nice regular box or something you can measure, like a box or rectangle, it's real simple. Length times width times height, okay? And you just take those measurements and just multiply them. And in this case, you get 24 centimeters by times 11 centimeters times 16 centimeters gives you 4,200 cubic centimeters, okay? Now, we also know that in 1 milliliter, there is 1 cubic centimeter. So we can easily convert that number to milliliter, because the units of density are normally mass in grams and volume in milliliters. Those are the most common units, okay? So, and not to say that grams over cubic centimeters is not used. I'm just saying the most common unit is grams or milliliters. So if you ever need to go from centimeters to milliliters, just keep in mind it's a 1-to-1 ratio. So I have 4,200 cubic centimeters is equal to 4,200 milliliters. Okay. All right, so that's the easy way to calculate a volume if you can actually measure something. However, not everything is easily measured. You have something that is not regular in shape, irregular shape. What we do is one way to do that is to measure the volume it displaces in a liquid like water. Okay. And so if, for example, we have a graduated cylinder, pressure, remember it's a cylinder. Okay. Little lip here, right? But it's got the marks here, okay? It's a graduated cylinder, measure volume. All right. So if we start off, for example, with something, a volume of liquid, most of the time it's water, and it measures at 20 milliliters. And if we take, in this example, a diamond and we throw it in here, well, just like being in a jacuzzi, right? You're in a jacuzzi, you know that volume of water is a certain level. Well, when you jump in, you walk in, that volume goes up. You have displaced and a volume, the volume you occupy the volume you have. That is the volume you have displaced, and therefore the volume in that jacuzzi goes up. All right. Now, there's a way to measure how much volume it was to begin with, and then to be able to measure how much volume it is after you immerse yourself completely in there. That difference will tell you your particular volume, okay? And so in this case, you start off with a liquid at 20 milliliters, 20.0, throw the diamond in there, and it goes up, volume goes up to 34.7. Now, the diamond does not have a volume of 34.7. Okay, it does not have a volume of 34.7. The 34.7 measurement is the final volume after you threw in the material. So the volume of the material is that difference from where you ended minus where you started. Okay, so 34.7 minus 20.0 says that diamond has a volume of 14.7 milliliters. Okay? That's the displacement it did. It does not have a volume of 34.7. All right, so that is the volume. And now we can go and take the weight of this thing, and we can actually determine the density for this diamond. So density is mass over volume, grams over volume, which would be 14.7 milliliters for this thing. Question is what state of matter is the element? Was carbon, if you recall from the periodic table, they showed the gases and the liquids and solid. Carbon is in the solid element state at 35 degrees Celsius. Obviously, in the moon, it would be a different state. On the moon, on the sun, I should say. Right now, how do we calculate the volume of a box? We did that already. Okay, as follows. Okay, so density. Okay, density by definition is that ratio of mass over volume. Normally, the units are grams over milliliters. Okay, but you will see units like grams over cubic centimeters, or you even see kilograms over kiloliters. And you'll find them even in English units, but we're not dealing with English units. We're working with metric units. So density is how much matter is in a given space. Okay. Now, which state of matter is the most dense? Well, that would be the solid. Okay. And the one that's least dense, obviously, is the gas. And if you think about it, if you look at that ratio, of mass over volume, the volume of the gas is much greater, okay? Without space in between them than the solid. Now, I'm gonna propose a question for you. Now, if we take say, loaf of bread, okay? Brand new loaf of bread. And this has happened to me hundreds of times when the boys, when they were little, we go to the grocery store, buy a loaf of bread, we get in the house, next thing we know, it looks like this. All right, so the loaf of bread, you started off with, and for argument's sake, let's just say the thing weighs 500 grams before it got squished. After it got squished, guess what? It still weighs 500 grams. Okay. Question is this: for these two loaf of breads, which is more dense? Which is more dense? Who has a higher density? A or B? Same material, put your thinking caps on. It's a loaf of bread. Kid got it, smashed it. Okay. Okay, we got the B's. The B's are correct. Okay, think about this now. It wouldn't be the same. Okay, be totally different. Because they both weigh 500 grams. And look at the volume here. The A, length, width, and height has whatever volume that is. But now that loaf of bread for B is a lot smaller. So the ratio of mass over milliliters, in this case, grams over milliliters, the ratio for B has gotten smaller, decrease, because it's got a smaller volume, okay, because simply its size. So now this ratio is going to be much bigger for B, because the denominator gets bigger, okay, think of it mathematically. If I'm dividing by a smaller number in the denominator, my number gets bigger. If I divide by a big number, I get a number small. Think about it. Is 1 divided by 0.1 the same as 1 divided by 2? No, not at all. Totally different numbers. So this scenario would be the B, because its volume decreases and therefore its density is much greater. Okay. So density changes. Now, let me ask you a question now. Yeah, I'm a big Hershey fan. Chocolate Hershey fan. Okay, I got a Hershey bar. obviously that Hershey bar has a X density, whatever density it is. But then, okay, I'm going to share with you. And so now I break it about right here. So I now got two pieces, okay, of the Hershey bar. Now, the density of this one and this one, we'll call this A and B. Okay. Are they the same or different? Okay. It's a Hershey bar. Sharing with you, I cut off a little slice over here, a little piece. Okay, I'll take the big one. I get A, you get B. But before we do that, we need to calculate the density. What happened to density? Exactly, they're the same. Okay. And the reason they're the same, again, because the ratio is the same. Like any number, any ratio, the ratio of 1/2, isn't that the same as, let's say, 2/4? Right? And so even though my volume changes here, so does my mass changes because I got less material. Okay, but that ratio remains the same for A and B. Okay, good. There's some examples of density. All right, again, we gotta hurry here. Now, different types of calculations of density. One straightforward, straight calculation. I got the mass, I got the volume, boom, I got the density. Okay, just simply do the mass. There are second type of calculations where I need to calculate either the mass or the volume given the density. If I have the density, depending on the question, I need to calculate the volume or the mass. Okay, for example, chloroform. Chloroform has a density of 1.48 grams. Okay, chloroform also does not mix with water. So if we were to put chloroform and water together, they would separate. It's like oil and water. The thing is, with the density as high as 1.48, it's going to be, its layer is going to be in the bottom and water will be above because chloroform is a lot more dense. Okay, has a density much greater than 1. So it would sink below water. The other aspect, FYI, chloroform used to be the old school of knocking you out when you went to operation. You need a little chloroform mask and you went night-night after a few drops. Now, a density, mass over volume, is a ratio, as any ratio that we've been working with now, all these conversion factors, ratio how much money you make per hour, how fast you drive per hour. It's a ratio, and we can write it down, write it as either grams in the numerator or grams in the denominator. Okay. And which one we use depends on the question and the units that we're looking for. If we are given X volume in milliliters, we will use the one on the right because milliliters cancel. We're trying to convert that to grams. If we're given X grams, we're going to use the one on the right, okay, because grams cancel. We're looking for units of milliliters. See how that works? Keeping track of your units. Okay, so in this example here, they're asking you to just do a simple density calculation. There's a necklace that weighs 484.56 grams and a volume of 25.64 milliliters. Well, what's the density? Simply, there's the equation, plug the numbers in, keep track of your sig figs. The answer is 18.9 grams per milliliter, okay? Another way to look at that is this, that every milliliter of necklace weighs 18.9 grams. Or for 18.9 grams of this necklace, it has a volume of 1 milliliter, okay? So now, that was a straightforward type of calculation, the first type. Now, the second calculation is you're given the density, okay? Now you're being asked to determine either mass or the volume. So like the problems we were just working, you write down what you're given. We are given 17.5 milliliters of chloroform. Okay. We are looking for grams. So that's my units that I'm looking for. Okay. I'm going to set up my factor here with milliliters in the denominator and grams in the numerator. Why? Because I want to get rid of milliliters and give me units of grams. That's what the question asked. So now I got this set up properly. The note about this is this. When you are given the density and you're asked to calculate the volume or the mass, you should only have one unit here. I see many times, for whatever reason, I get grams per milliliter or milliliters per gram as my units, and that's not the case, okay? Our units cancel the way we set this up. Now you just simply plug in that number in the calculator and you're good to go, okay? There it is, units cancel, and do note that density is a measurement, okay? So it could play a factor in with respect to your sig figs. But any density is a measurement, so they could be a factor. In this case, the answer is in 3 sig figs. Note the units that cancel like they should, leaving me with 1 unit because that's what the question is. How many grams are there in 17.5 milliliters of chloroform? This sometimes helps where you may not have a balance to weigh out a mass, but you have an instrument or piece of equipment that you can measure volume. So you can measure 17.5 grams, and that using the density determine how many grams that equates to, which then you can use for your calculations down the road. Okay. It's one advantage of using density. The next one, if we're going from milliliters to grams, we multiply by density. In this case, they want to know how many milliliters. Okay, so we're looking for volume, and we are given 0.035 grams. Okay, and we want grams in the denominator, milliliters in the numerator. Okay, so 1.48, 1 milliliter. Check my units. Units cancel. Grams, leaving me with single units of milliliters, which is what the question asked for. Okay. All right. And in keeping track of your sig figs, and that's the volume of 0.0735 grams of chloroform. Okay, those are the type of density calculations. Either you calculate the density directly, or given the density, you're asked to determine either the mass or the volume of a given amount of material. Okay. Going to shift gears a little bit. We're going to talk about temperature / energy, and it's pretty self-explanatory here. You know, we use the term temperature, but remember, temperature is directly proportional to energy. You put energy into the system, like heat, we're going to up the temperature a little bit. And so what we can say that molecules, as we heat them up, obviously they're going to start moving faster. And simply because they have a lot of high energy, they got higher energy compared to cold molecules that slow down simply because the energy that they have is low. Okay. Temperature, obviously, we measure with the thermometer. Okay. And we have 2 scales. Actually, or correct that, 3 scale. Okay. The scale that we all tend to live in with respect to temperature, and that is Fahrenheit. That is the English unit. And then we have Celsius, and then we have a new unit that we introduce here. You may not be familiar with. We call that Kelvin. Kelvin. named after a British scientist, Lord Kelvin. Now, the thing about Fahrenheit and Celsius is they will go to infinity up the scale or down the scale. Their number never ends. So the scales go to infinity for both the Fahrenheit and Celsius. With respect to Kelvin, it does not. Kelvin stops at 0. This represents 0K. 0K is known as absolute zero. That is the temperature where it has been proposed that all matter stops moving. There's no movement and all atoms are frozen in time. We haven't been able to reach that. We've come close, but we haven't reached that yet. We do know that getting down to those low temperatures, there's a whole new chemistry occurring down there, a whole new different properties at low temperature has occurred. Getting down to low temperatures also causes things to be like conductors with no loss of electricity. That's a whole nother story. Okay. Anyway, those are the units we utilize to measure temperature: Fahrenheit, Celsius, or Kelvin. Now, the thing about Kelvin, Celsius and Kelvin are related in the sense that to go to Kelvin, we need Celsius, okay? And to go from Celsius to Kelvin, those are connected. Fahrenheit is not connected to Kelvin, okay? It is not. So if you start at Fahrenheit and you need to get to Kelvin, you need to take your Fahrenheit and convert that to Celsius first, then convert that to Kelvin. Okay. So, and we're going to explain how to do that here in a second. So, talked about absolute zero. Now, here's the equation to convert from Celsius to Fahrenheit. You don't need to memorize them. Why? Because they're in your shades table. Okay. So, if you have Fahrenheit and you need Celsius, you simply subtract 32 from your Fahrenheit and then divide it by 1.8, and that gives you the temperature in Celsius. Okay. Then if you have Fahrenheit, if you're looking for Fahrenheit and you're looking for Celsius, you have Celsius, you multiply Celsius by 1.8, then you add 32, and that gives you Fahrenheit. With respect to Kelvin, you got to take your Celsius and do a simple thing and just add 273, and that gives you the temperature in Kelvin. So like I said, I can't go directly, cannot go to Kelvin. I have to go through Celsius first, then I can go to Kelvin from there. Okay. So with that in mind, you might try this. Temperature in Phoenix can get up to 115 Fahrenheit. Plug those numbers in, and you should get 46 Celsius and 319 Kelvin. So give that a shot, so you can come up with those answers. And if you're not, we can bring it up the next meeting we have on Thursday, and we can go over it. All right, which brings us to heat/energy. Okay. So if we look at the two beakers on the right-hand side, the two diagrams of two beakers, you can see what looks like a thermometer inside a liquid, A and B, and it's measuring the temperature, and both of them are at 100 degrees Fahrenheit. Okay. And the question says, which of the two beakers has higher temperature? And I'm like, well, they both do. That would suggest maybe they're the same material. I don't know. There's not enough information, but the temperature on both beakers is the same. Okay. But then the second question says, which has a greater amount of heat? And the answer is, and the question is why? They're asking you. Think about this for a second. You know, let's say you got a big pot on the stove and you're going to boil some water to make a big old bag of spaghetti. So you got this big old giant container of water. And then you got a little smaller one where you're gonna make just a little bit of cup of tea. Now the question is this, which would you rather have spilt on you? Zero, none of them, obviously, but if you had a choice, which one would you rather pick? Obviously, the small container, right? Because there's less material. There's less atoms, of course, there are less atoms, so I would have select the less material to spill because there's less atoms, less energy involved. In that example, and it has the less amount of heat. This is a phenomenon that occurs even out in the Pacific. It's called the El Nino La Nina. A lot of times I ask students if anybody heard that. You might hear it in the news, weather news, but it's nothing, it's not a hurricane. And I get all kinds of answers, but it's nothing more than a body of water out in the Pacific. El Nino just happens to be a larger body of water than La Nina. But that body of water is humongous. It's very big. And what it is, its temperature may be a little bit higher, maybe 1 or 2, 3 degrees higher than the rest of the ocean. But it has so much energy involved there because the magnitude of water that it has a drastic effect on the world weather. A lot of energy out there in the oceans. Okay, heat transfer. Thing to remember about energy, whether it be heat, but any energy, is that Mother Nature is lazy. It's not gonna spontaneously, energy or heat is not gonna be spontaneously be given to something. In other words, if a chunk of matter has energy, and that energy is at a higher state than its environment, and that energy is going to go from high to low. It's going to be transferred to where the lower energy is at. It's a gradient, okay? High to low, that's where energy goes. Can you go the other way? Yes, you can, but it takes energy to bring it back up, okay? But spontaneously, energy always goes from high to low. So if you got a cookie and we cooked it out here and the transfer heat and you take a cookie out, well, what's happened here, who loses the heat? Obviously the cookie. The cookie is hot. Your hand gains the heat and that's why it burns, okay? Because it gained the heat that the cookie had. Even more is that the temperature of the cookie drops as your hand touches it, because it transfers that energy, and the temperature of your finger goes up because it picked up the energy. Okay, and this is true here for a piece of metal that is placed in the freezer, and then you place the metal in the bucket of water. Temperature of the metal increases, decreases, or stays the same. Well, it increases. Okay, because it was cold, you put it into a hot container, the energy transfers from high to low. Okay, the same is true if, let's say, dead of winter, nice and cold, you're in there taking a morning hot steaming shower, nice and warm, right? You're probably experienced this. You get out of the shower, you step out, and you are freezing because it's cold, right? So what do? You jump back into the shower to warm up. And you do warm up for a little bit, okay? So think about this. You're in the shower to begin with. You're equilibrated with the heat of the shower, steaming hot. Okay, so you're a high temperature, high energy level. You step outside where the energy level is lower, the environment, right? And then the energy that you have is released through the environment. So your temperature drops. So what do? You jump back in the shower. Now your temperature is lower than the environment. So now the energy of the shower goes back to you and you get warmed up. So you can go back and forth. Eventually everything stabilizes to room temperature and you get to some ambient temperature. Thomas had a question.
Yes, Professor, that really
Oh,
confused me because when I learned it in biology and the teachers explain it, and then when I apply it, when I see it in real life, it doesn't make sense.
okay. Well, you have you been to like a restaurant and you go and they get a mister?
No.
Do you
What is a
never,
mister?
have you seen like a water?
Oh yeah, the thing that yeah.
Yeah, and when you walk in, doesn't it feel cooler?
Yes.
Yes,
Why is that?
because the water is taking the energy, the heat away from your body and cooling you down. Okay, you are a higher energy level than the water, and water is a good example where it will pick up energy. That's why El Nino on the Pacific it picks up so much energy. The water is a good. There's a name for it. I'm having a senior moment. Specific, not specific gravity, but it will absorb that heat. And so when it rains, all that moisture is picking up any heat that's around it, so things cool down.
So
Okay,
so it explained that and heat transfer rather than hydrogen form then.
and
So, so the way when it rain, it's more like a heat transfer rather
yes,
than oh I see. Thank you.
just a heat transfer. Just remember, energy goes from high to low. So wherever you're at,
Ah,
if you're a higher temperature, you're going to lose that energy and move it to the low. A good
I
example,
see.
if you make a cup of tea or a cup of coffee and you put it on the kitchen tabletop, you come back an hour from now, it's no longer hot, right?
Mhm.
Yeah, it's warm, it's now cold to the environment that it was in because the temperature went from high and dissipated into the environment.
I
Okay?
see. You
So it's
transfer.
heat transfer, exactly.
Oh, I see. Thank
Yeah,
you.
yeah, no problem. And so in this case here, we're almost done. Temperature of the water decreases. Okay, so one decreases. So if you got a cup of coffee or a cup of tea and it's way too hot, the best way to cool it down, you can throw ice in there if you want, but that can dilute your flavor. But just throw a couple of silver spoons in there, metal spoons that are cold. Well, obviously the heat goes from the hot coffee or the hot tea and it gets transferred to the metal and your temperature drops. Eventually, all that goes to the ambient temperature, whatever ambient temperature you're at. Okay. All right, well, that is so much for this chapter here, but okay, don't forget, you gotta examine Thursday. Okay, be familiar with your sig figs, and we're gonna use sig figs throughout the semester. And, sig figs are just something that we in science use all the time. We can't just think of it this way. We cannot be more accurate in presenting our data than the least accurate figures that we start on. It would be nice to be able to, give you all that accuracy with the digits that a calculator have, but you're not that accurate with the instrument that you use to take that measurement. The question was the homework, the homework should show you that after your last attempt. If it's not, I need to know because it shows you the correct answers in the homework. Okay, if not, let me know. I may have to find out what's going on with Canvas. Okay. I'll go in there right now after we're done here and verify. All right. Ladies and gentlemen, that ends chapter 3. 3 chapters down. 12 to go, right? All right, next chapter, chapter 4, we're going to get back into chemistry. Right now, we're going to do mathematics, which, by the way, I put in my back here all the prefixes, FYI. And we'll be talking about going back to chemistry, talking about the atom. and get deep into that. Okay. All right. Any other questions? I'll find out about that homework, but you should be able to see the answers after your last attempt. And come Thursday, if there are no questions about chapters 1 to 3, I'll jump right into chapter 4. All right.
Thank you.
Thank you, guys. You guys have a be safe out there, and see you on Thursday, unless there's a question.
Hi, I have a question, Professor.
Sure.
I just had a question about the Canvas homework that we turned in for chapter 2. I
Uh-huh.
have a couple of partial rounding points that I did. And it doesn't show me which is wrong on there. It
Okay.
just flags it as partial. And I'm just kind of getting confused because like I thought I did my rounding right. Along with the sig figs, and there's one that I did have a question about. It says perform the following calculations and round your answer correctly. It says 978 plus 22.5.
Let me do this. Let me write this now. Okay. So you have 928.
978.
Oh, 978.
Uh-huh.
Okay. 978. Okay.
Mm-hmm. Plus 22.5.
Okay. 22.5.
Yes, so I get 1000.5.
Okay.
And I know that you're supposed to, since it's addition, you go off of how many decimal places. So since 978 doesn't have any decimal places, technically we won't have any decimal places. So that leaves us with rounding up to 1001, right?
That is correct. Okay. So,
Okay,
because looking at your neighbor there, so your answer should be that.
right. So there's a lot of rounding that I thought I got right, but are getting flagged as partial points. I don't know if it would be okay if you could take a look at some of those that I turned in.
Okay, well, let me find out, because sometimes if this is correct, so you wrote that, then that'd be correct. So the partial could be from another part of that question.
Okay, yeah, I'm just getting really confused because I went off of even with the multiplication and the division, I went off
Okay.
of the rounding and I
Okay.
went off of the sig fig rules,
Yes,
but it's
What-
just a little,
let me do this. Let me, okay, chapter 2, is it one, is that the activity or the homework?
it is
There's a homework.
The
Oh, sorry.
homework?
the homework, yeah.
Okay, so all that should be, let me go in there and find out why it's not showing you the answers. It should have been showing you the answers. Now, have you done both sequences or both attempts? I lost you.
Oh yeah, I did both attempts.
Okay. And. Okay.
Professor, I think they changed the question because I think that's the question number 5, right, Samantha?
There's the
For
question.
number 5, let me see. Question number 5, 97.8.2, and then if I go to my, so I'm trying to open up my second attempt here. Attempt
Okay,
2.
let me take a look over here myself.
No,
Okay,
question number 5 on attempt 2 is the same.
okay,
I'm sorry. So what's the correct answer? Because I did both attempts and I still got it wrong on both.
Okay. That's what I'm checking it right now. We're looking at homework number 2, right?
Yeah.
All right, so I gotta make sure and find out why it's not showing you the answer. And then give me 1 second. Let's submit to. Okay, I see what happened. Okay, for this one, give it a second and then get out of your question number 2, chapter number 2. Okay, and then go back in and let's see if it shows you the answers now. It wasn't toggled to show you the answers for some reason.
Yeah, I can see them now.
Okay, and I'm gonna go in there and check number 1 to make sure. Okay. Number 1 is now open, should be. All of these, for some reason, I'm gonna have to go into every one of these and correct that. And I'm gonna move, check chapter 3. Okay. Okay, so chapters 1 to 3 have been fixed. So you should be able to see your correct answers now.
Okay.
Go back in there. If you're in there now, exit that homework and then go back into it, and it should allow you to see it now.
Okay.
Have you done it? Did it let you go back in?
It's working now. It shows us what's
Okay.
correct and
All
what's
right,
wrong.
well, let me make a note to myself because all the other chapters did not come across when it was copied over from the base. What we do is we create the Canvas course in one central location. And then once all the classes are done, we're all ready, then we transfer it over to our section. And something in the transfer may not have clicked right with Canvas. So note to self, I need to go through chapters 4 through 15 to make sure it shows the answers.
Okay. And I
So-
have another question.
Sure, let me write this real quick before I forget. 4 through 15. All right. Go ahead.
So on the question number 5 for B, I got the 960.8, and then it says to round your answer correctly. So I rounded it up to 961.0, still keeping my my 4 sig figs. No, I'm sorry, 1 decimal place. Is that correct? Should I have even bothered to round that up, or?
Okay, let me write the problem. What was the problem saying?
It's 978.2
978.2.
minus 17.36.
Okay, and you got,
I got, I believe 960.8. I believe. Let me type it back in. 978.2 minus 1736. Yeah, I got 0.84. So I was like, I think I just round this up to 961.0.
no,
Keeping it.
okay. Okay, keeping, so 960.84, okay?
Mhm.
Now, how many decimal places here?
1.
And how many here? The next one? 2. So your answer should have what?
1 decimal place.
So that one, so that means you gotta look at, what do you do to the 8? You keep it at 8 or move it up?
Oh, okay. So yeah, you would leave it.
Okay? There's one decimal point placed just like that one. Okay?
Oh,
Remember, when you add and subtract, you think decimal places all the time, okay?
mhm.
For adding and subtracting. When you multiply and divide, you think sig figs.
Mhm.
Okay?
Right.
So if I were multiplying or dividing these two numbers, then I would have 4 sig figs in my answer. Okay?
Mhm.
But I'm subtracting, so I look at who's got the least number of decimal places, which is that one.
Okay. So
Okay.
I think my train of thought was, oh, there's supposed to only be 1 decimal place. So I focused only on the 8 and not the 4. So therefore I rounded to 961.0. Trying to
Okay.
keep that zero, that trailing zero there with the decimal to keep it.
Oh, yeah, okay.
So that's what I was thinking.
Yeah, no. Okay, don't, I see what you did. Okay, but no, when you add and subtract, that's why when the question says, I got a call from, when you add and subtract, when the question says, think about, I'm gonna restate that. When the question says to put your answer in the correct sig figs, okay? The first thing you should ask yourself is, what is the mathematical function I'm doing? And that's what this is all about right here, that one or that one. Once you know what mathematical function you're doing, then you focus on either decimal points or the sig figs,
Mm,
okay?
okay.
So here you're doing subtraction, so you focus on decimal places. Okay,
Okay. Yeah,
Alright.
I got it now. Now I know why I got some of them partial. Okay.
all right, okay. So you all should be able to see your answers now. And if you still have a question, shoot me an email, or we can bring it up on Thursday and go over it again. Okay? And there's a question about the ruler.
No, I think I see why I got it wrong.
Okay. All right. Okay, remember the ruler, depends on whether you got one decimal place accuracy or 10 place or the 100 place. And depends on the accuracy of the ruler. Does that make sense?
Yeah, I see why I got it wrong both
Okay.
times.
Okay,
Thank you.
hey, no worries. No worries. Okay, all right. All right, well, we'll see you on Thursday, guys. Okay, take care. Okay, any more questions? We're good?